In this lesson, we're going to have a look at how the temperature changes as a substance is heated from the solid through to the liquid and then into the gas states. We're going to examine what is called the temperature time graph for these changes. So on our graph, we're going to plot the change in temperature in degrees Celsius with the time in minutes, for example. Now we're going to use an imaginary substance. It's a pure substance, and the changes that occur to this substance as it's being heated is typical of any substance that is a pure substance and exists in the solid, liquid and gas state. So what we're going to do is we're going to heat the substance and we're going to record its temperature. Now we remember that the temperature of the substance is a measure of the average kinetic energy of its particles. Now these particles in the solid are moving around, they're vibrating around a fixed position, and at the moment we'll say that the temperature of the solid is, say, at room temperature. It's at 20 degrees Celsius, and so what we're going to do is we're going to start heating the solid. Now as we do that, energy is going to be transferred into the solid and it's going to make the particles vibrate around more. Their average kinetic energy is going to increase. So while we're heating the solid, we'll see that the temperature on the temperature time graph starts to increase, and it will increase in a linear fashion. Now we remember that from the last lesson we can liken the conditions inside a solid lattice to a kind of high security prison, where you've got prisoners which are trapped in cells. They can vibrate around within those cells, but they can't escape the cells. Okay, so again, what's happening here as we're heating up that solid is the atoms, or the prisoners if you like, are vibrating around more and more and more, but eventually what's going to happen is some of these prisoners are going to acquire enough energy to escape from their prison cells. They're going to acquire enough energy to escape from the lattice. So they're vibrating around more and more, and then suddenly, yippee, the particles will start to escape. Okay? And more of them will escape into the liquid state as they acquire enough energy to break through this solid lattice. Now, as soon as this starts to happen, the energy that was being used to help increase the kinetic energy, or the average kinetic energy of the solid, is now being used to help these particles escape into the liquid state. So as a consequence of that, because the energy is being used to help them escape, the average kinetic energy of the particles in this state actually remains constant during this change in state, during this phase change. So when we look at the temperature time graph, it will look like this. Okay, it will be flat. During this change from the solid state into the liquid state, the temperature remains constant. Now we call this temperature the melting point of the solid. And while the solid's melting, its temperature remains constant. Now eventually all of these particles will have changed from the solid into the liquid state. So now we have a new kind of prison, if you like. And we say that the particles are held within the liquid structure by what is called the surface tension. Okay, so this is a kind of low security prison. Okay, the particles are now free to move around within this prison, but they can't escape through this prison wall unless they have sufficient energy to do so. So what's going to happen now is we're going to continue heating those particles, and this time they can move around wherever they want within the liquid structure. As with the solid, there are a whole load of random motions moving at different speeds in different directions, and so gradually the average kinetic energy of the particles in this liquid state begins to increase. Okay, like that. So now the temperature is increasing because their average kinetic energy is increasing, but eventually these particles are going to acquire enough energy to break through the surface tension and enter into the gas state. Okay, so we've got the same word again. They're escaping from one state into another. And then just as when they were escaping from the solid state into the liquid state, when they're escaping from the liquid into the gas state again, the energy that enters the liquid is used to help these particles escape rather than to increase the average kinetic energy of the particles. So all of this energy from the Bunsen burner, or whatever it is here, is helping these particles escape into the gas state. As a consequence, the temperature of the liquid remains constant. So we're going to get another flat bit here. And this is known as the boiling point of the liquid. So we have the melting point and the boiling point. And so when the liquid reaches the boiling point, the temperature remains constant. Okay, let's just summarize this temperature time graph to make sure that we've got this. We've got a substance existing in three states. It's in the solid state here, it's in the liquid state here, and in between and during this phase it's moving from the solid state into the liquid state. We call that melting. And then during this phase here it's moving, or it's changing from the liquid state into the gas state. So while the solid's being heated here, what's happening is the energy from the Bunsen burner is being used to increase the average kinetic energy of the particles and therefore increase the temperature of the solid. When we get to this point here, the solid starts to melt, and while it's melting, this energy now, instead of being used to increase the temperature of the solid, it's now being used to help particles escape into the liquid state. And during this phase, the temperature of the substance remains constant. We call that the melting point. Then once all of the solid has changed into the liquid state, then the energy is used once more to increase the average kinetic energy of the particles and the temperature of the liquid, until we reach the point where the particles start escaping again into the gas state. And when that happens again, the energy from the flame is now being used to help them escape rather than increasing their average kinetic energy and therefore increasing the temperature of the liquid. So the temperature of the liquid remains constant during this phase until all of the liquid has changed into a gas.